Okay, welcome everyone. Welcome to this webinar from Telops. Today, my colleague Joseph Carrick will be discussing the sub-microsecond exposure for infrared imaging, especially for hyper-velocity applications. Here's Joe. Hello, Joe. My name is Antoine Dumont. I'm a field application engineer based in Quebec City, the headquarters of Telops, and Joe is based in the US. So I'll just introduce Joe briefly. So Joe has a master in imaging science from Rochester Institute of Technology, and now, just like me, he serves as a field application engineer for Telops. So he's located in Western New York, and he works to develop and advance applications and the technology in general for Telops in infrared imaging for high-speed broadband, multispectral, and hyperspectral systems. So today, the focus will be on the sub-microsecond exposure for infrared imaging. So quite a niche topic. It's very, very interesting. Some work that Telops has been working on over the last few months or year even. So before we get started, we always like to have a little poll to understand the audience that's with us. So I'll submit a poll just trying to understand your experience with infrared technology. So you should be able to see the poll right now. So you can actually just click on your screen. So let us know if you do have a direct experience with the technology, you've considered it. You do have direct experience with infrared imaging, with collecting data, etc., or if you even consider yourself an actual expert. So I'll let the poll go for maybe another 20 seconds or so. Considering the niche topic of today's webinar, I'll be very interested to know the people that we have with us. All right, let's take a look at what we have. Very interesting. So not a single person that actually said that they don't have any direct experience. It would have been very interesting to have people that are just interested, but it's not surprising considering the topic today. So you have considered it, you do have direct experience, or you do even consider yourself experts. So that's great. We expect some very interesting questions at the end of this webinar. So let me hide the poll. And I'll let Joe jump in and start our webinar today.
Thank you, Antoine. So again, my name is Joe Kroc. I am a field application engineer located in the US in Western New York. And today I will share with you some of the work we've been doing exploring sub-microsecond exposures on our cooled infrared cameras for hypervelocity applications. So a quick overview, we'll do a quick Telops introduction, and we'll talk about our fast IR cameras, which is the type of cameras we use for these applications. Then we'll talk about the need for ultra-short exposure imagery, smear radiometry and signal levels, temperature, speed, and triggering. And finally, I'll talk about the products we currently offer and some of the custom projects we're working on with our customers and contacts. So Telops was founded in the year 2000 in Quebec City, Canada. We're almost 25 years old, just about to hit that anniversary. And we now employ about 100 people, many of whom have advanced degrees. We're a company of engineers and scientists, and we love working on advanced problems like this. So I'm going to sound like a broken record by the end, but please do reach out to us. We would love to work with you on your specific needs. We have established ourselves as a world leader in infrared imaging solutions, and we've also, as of 2023, joined Exosens Group, which is a leading infrared technologies company. We offer a full suite of cooled scientific infrared cameras, as well as multispectral and hyperspectral cameras, as well as solutions for aerial methane detection and quantification. So these are some of our cameras. The hyperspectral and multispectral there on the left give you more spectral fidelity. We won't be talking about those so much today, but the high dynamic range and high performance fast cameras are what we will be talking about. And I will go into a little bit more detail on those after we talk about some of our common applications. Ballistics, obviously a fast camera application, same for combustion, experimental mechanics. Gas detection and mineral identification are more multispectral and hyperspectral applications. Then we have signature, additive manufacturing, non-destructive testing, all bread and butter high-speed applications for Telops. So again, back to our fast cameras. They are cooled broadband infrared cameras, fastest available on the market, up to 3,100 frames in full frame mode, but tens of thousands of frames in sub-windowing. That doesn't necessarily matter for high-speed applications, as we'll learn a little later on, but these are cooled, calibrated radiometric instruments. They have a 4-position motorized filter wheel for the application of neutral density filters to unlock higher temperature calibrations, and we offer them in the shortwave, midwave, and longwave. A couple of the cameras we're going to talk about specifically today include the midwave, the M3K that you see there in the top right. It is a 320-256 pixel detector with large detector pixel pitch, which we'll talk about why that's important in a little bit. And this camera has a pretty good NETD, a pretty low exposure time, just under 1 microsecond off the shelf. And again, it is the fastest infrared camera available on the market, although we will see why that's not necessarily important for hypersonic applications in a little bit. Then we have our HD and longwave cameras, which we'll also be talking about today. Specifically, the M3 SHD is a massive 1920 by 1536 pixel array. You did give up pixel size there. Detector pixel pitch is only 10 microns for that camera to fit those pixels on that FPA, but it is a very powerful high definition option. And then we also have the longwave series. Our longwave cameras are 7.5 to 11.5 microns. Specifically today, we're going to talk about the V350 a little bit. One more camera, something that we haven't explored yet, but is a new and exciting system, is the HDR M700. It is an all-new high dynamic range system with new electronics that are able to improve the dynamic range performance of a single shot, a single exposure with a single optical path, such that you can see almost 900 degrees C in a single image. This is a new capability for IR cameras. It's the first of its kind. A traditional IR camera is maybe able to see 150 C, 250 C in a single image, but this camera drastically improves that. And these new electronics, this new readout, is something that we haven't explored for these hypersonic applications yet, or high-speed applications, high-velocity applications, I'm sorry. But it is something we're excited about, and we will be exploring it in the near future. So let's just generally talk about the need for ultra-short exposure imagery. And here's a quote from one of our engineers, Fabian. Acquiring clear radiometric imagery of a fast-moving target requires perfect synchronization, a short exposure to limit the motion blur, and sufficient signal-to-noise ratio. What does that mean? Well, when these targets are moving at their high speed, we need to make sure that our exposure time is short enough that we limit motion blur. You can see there on the right, as you decrease exposure time for high-velocity projectiles, your motion blur will lessen. And the idea is that you want stop-motion imagery if possible. It's not always possible, but it's what we shoot for. And that will improve our ability to radiometrically calibrate our data and give better results for the type of applications we see this need. And so those are primarily, first and foremost, hypersonic research. Hypersonics is the term used to describe projectiles traveling at Mach 5 or higher, 5 times the speed of sound. And typically we see this with projectiles, ballistics, thermal protection systems for reentry vehicles, air propulsion. It really runs the gamut, and these applications are quite diverse and different. So often the solution is not the same across this research field, but we have seen a lot more interest from hypersonic ranges, high velocity wind tunnels, that sort of stuff in those sort of researchers in the last few years. Separately, we've also seen a lot of interest in cold spray. Cold spray is sort of an emerging additive manufacturing technique that uses high velocity gas to project and impact fine metal powders onto a substrate, building up some kind of sample or product. And it's not actually the buildup of the material that we're interested in, but it's the in-flight particles that need ultra-short exposure imagery. So we'll go to the next slide here and pull this figure back up. Those are actually copper metal pellets in flight that you see here in this figure. And as we can reduce the exposure time, we can limit the smear of those particles in flight, which allows us to better estimate their size and temperature. Of course, that could be done in post-processing, but it's far better to have lower exposure and limit the smear. And with that, how do we calculate smear? Well, we have that pretty simple equation there. Exposure time equals smear over object speed. So a couple of examples. Let's say we had a requirement of 1 centimeter smear at 1 centimeter GSD pixels. If your object is traveling at Mach 10, 10 times the speed of sound, your exposure time would need to be 2.9 microseconds. And that doesn't sound so bad. So what can we push it to as an example too? At Mach 10, 1 microsecond exposure time, that's the standard minimum for most of Telops IR cameras. We can get 0.34 centimeters smear. Sounds pretty good, right? Yes, until you consider that most of the requirements we see often have maybe 1/10, 1/5 of a pixel smear requirement. So if it's 1/10 of a 1 centimeter pixel, your actual exposure time that you need to capture that would be 0.29 microseconds, which is exactly why we're doing this research and exactly why we're trying to push our cameras to go to these ultra short exposure times under 1 microsecond. So here's one more example before we get into the nitty gritty and all the trade-offs that need to be made to do that. Does anybody know what this is? I know you can't answer me back, but it is actually a projectile, a 120 millimeter shell shot from a 120 millimeter gun out in the desert in New Mexico. And the concept here is that as this projectile moves through the scene, it does not stay on the same pixels during a single exposure. It actually spreads out across. It contributes signal to multiple pixels. It smears. And this is sort of a nice visual representation you can see here on the right. That's the picture of the particle. Obviously, this is a sequential set of images. But up at the top, it's zoomed in. That's the smear itself. And then the line profile that I've added, that green line, contributes to the temperature plot underneath, where you can see that the projectile probably was in those initial pixels that look blue there, and then moves during the exposure towards the left. And so we're trying to lower our exposure times again to limit that smear primarily. But what do we have to do? What limitations and trade-offs are there to get under 1 microsecond to try and limit that smear? Well, we have to talk about radiometry and signal levels. We have to talk about pixel size and well depth, temperatures and well filling, saturation, and finally speed and triggering. So there's quite a lot to consider. And again, I would encourage you to reach out to talk to us about your specific application. We are a team of engineers that loves working on this stuff, and it's not a one-size-fits-all solution by any means. So let's first talk about radiometry and signal levels. Why is this important? Well, who knows about Planck's law? I hope all of us, based on the amount of experience we have in thermal imaging. But the main concept here is as you increase in object temperature, you get more signal radiated. And the peak intensity of that signal also shifts towards shorter wavelengths. However, there's a time component here. So when we limit the amount of time that we're exposing for, we are drastically limiting the amount of signal that we can collect, even if we are in bands where there is more signal, something like the midwave or shortwave. So what does that mean? Well, we have to consider pixel well depth and pixel well filling. All of our detectors collect photons, right? They convert them to electrons that are captured in the readout electronic wells. And typically, our error specifications on our normal calibration say that we want well filling between 10 and 90%. That's to avoid adverse effects at the outer ends of that range. You can get some nonlinearity, you can get some bad signal to noise effects. And with short exposure times, ultra short exposure times, we will struggle to fill these wells to 10%, even with high temperature targets. In some configurations, we'll even struggle to get just a couple of percent well filling. And so what we want to do is we want to try and select cameras that have small wells and large pixels. The pixels is, they are the size they are on each of these detectors, but some cameras do have multiple well depth options. And so that's something we'll talk about in a little bit when we look at the list of cameras and the work that we've done. Next, we need to talk about temperature, well filling, and saturation. So the problem, of course, with all of that, if we take one step further, is that there is a narrow band of acceptable signal levels between the minimum amount that we would need to properly fill the wells for good signal to noise and the maximum amount that our readout electronics can accept without experiencing photocurrent saturation, which is just as bad as overpixel saturation, which is not necessarily, overfilling saturation, which is not necessarily a problem for these types of measurements given the low exposure time, but we need to avoid all types of saturation and keep good well filling for decent signal to noise. So certain detectors also perform differently when we get down to these low exposure times, and they may benefit from different things, including different spot size to try and improve our signal to noise, get the good well filling, while at the same time not allowing photocurrent saturation that you would see if you had a larger spot size on your detector. So finally, here on this slide, I do want to talk about this plot in the bottom right. This is an estimate for the 2 different well depths that are available to us with our M3 SHD system with a broadband filter modeled for high and low gain is how we've labeled that. And the important thing to understand is that as we accept a high gain, we may unlock higher well filling, be able to hit our well filling targets faster at lower temperatures, but what we have to trade for that is dynamic range. We will not be able to see as many signal levels as wide of a range of temperature in the same image if we use high gain mode. So again, I'll sound like a broken record on multiple things throughout this presentation, but it is sort of application to application. You have to make specific choices based on your needs. I will also add at this point, I guess, for the M3K and the M3 SHD cameras, we have explored fully going below 1 microsecond exposure. And some of the things we're starting to see as we develop custom solutions for a few of our customers is that the performance is not necessarily uniform below 1 microsecond exposure. It's not the same as above 1 microsecond exposure, but it's not even the same at the discrete values we can set the exposure to below 1 microsecond. For example, at 0.4 microseconds exposure, the detector might not perform the same as at 0.6 microseconds exposure. And so the work we're doing currently to work on that is to try and come up with a scheme for a supplemental multi-point calibration to our standard global calibration that would be able to rectify and still give you good radiometric accuracy and performance at those discrete exposure times below 1 microsecond. So finally, before we start talking about which cameras and why and the work we've done, we have to talk about speed and triggering. And the first line there is pretty interesting. Frame rate is irrelevant. That doesn't sound right, but it is. The speed at which these projectiles move, you get 1 frame. By the time you wait, even at the fastest IR camera frame rates, thousands of frames, tens of thousands of frames, your projectile would move out of the frame by the time that you take that second shot. And so what that means is we need to have a well-engineered and precise triggering system to sort of take our snapshot right while the projectile is in frame. Luckily, Telops cameras are well-engineered to do that already. They do accept external trigger TTL signals and low-voltage TTL by BNC, and we do have well-characterized trigger jitter. It's around 300 nanoseconds, and it can be characterized on a system-by-system basis a little more accurately than that. And so here we are, sort of getting to the end of my pitch here, at least the culmination of it. Potentially fast horses or candidate cameras for these types of measurements. The ones we've used so far, the ones we are currently developing, include the M3K and the M3 SHD. And why we've chosen these cameras is for the M3K, the pixel pitch. It's got large pixels again to allow us more signal at these low exposure times. Has a good F number. This is something I didn't mention yet, but obviously larger aperture, more signal, same concept. The lower F number is great there. And it also has these multiple well depth options, including a high gain option at 150 KE, which is proving to be relatively beneficial in this space. The other camera we've done a lot of work on is the M3 SHD. This is our high definition option again, 1920 by 1536 pixels. You do get smaller pixel pitch there, but it does have pretty decent well depth options. And again, we've characterized that camera below 1 microsecond and are currently working on a multi-point calibration to rectify the detector performance at these ultra low exposure times. The last camera here I'll mention is the V350. That is our long wave option. That's sort of what we're going to be looking at next, especially for cold spray applications where you don't have these high temperatures at all. You will need a way to get more signal into your detector, and long wave, as we saw back on the Planck's law chart, it's expected that we will be able to get more signal and might be able to do something for lower temperature applications. Finally, here I do have the two of our newer cameras. The HDR M700 and the M2K UD are both sort of cutting edge detectors, specifically the M700 HDR. We see a lot of promise with. We expect that camera in the future will be one that we develop as well for these applications. So finally, a bit of a conclusion here. Available now, the M3K, the M3S HD, and the V350 all have 1 microsecond exposure or less off the shelf. We have several IR cameras, others included, that have that 1 microsecond exposure specification. You can inquire today about high gain, low well depth options for the M350, or sorry, the M3K, the M3S HD, and the V350. Those are things that our engineering team can work with you on. And looking forward, we are actively working on R&D, firmware adjustments, that multi-point calibration I talked about, and we will look to explore what is possible with our next generation detectors, like the one in the M700 HDR. So that is the majority of my presentation. I hope this was interesting to you. I know we had a lot of high level thermal imaging experts here. This is sort of a mid-level presentation, but it is intended to be general in the sense that these applications require very, very specific camera configurations, very specific changes to the standard cameras. And so we encourage you to reach out. We enjoy working on these problems. We're happy to work with you to talk directly about your application needs and to try and devise a solution that can achieve your measurement goals. So one last thing before we take some questions, our new Exosens website, the Telops website has been integrated into the Exosens website. That's what it looks like there on the left. If you scroll to the bottom of that page, you'll find the resources tab. And there we have all of our resources, all of our past webinars, application notes, and the sort that you can search with key terms or by brand. There you see some cold spray applications. We also have some high velocity. This webinar will be there in the near future, and we will always be looking to add more content. So thank you for listening today. We appreciate you being here, and we will take a second to look at the question box to see if there's any questions. Please feel free to type some. And again, you see that sales email there. Our email that would reach Antoine and I immediately is FAE@telops.com. That stands for Field Application Engineer. FAE@telops.com. We'd love to talk to you about your measurement needs.
Thank you very much, Joe. That was a very insightful webinar. If you do have questions, just look down in your tab for the GoToWebinar question box, and let's see what we have here. So we do have some questions coming in. So first one being, what are some key elements that set these products apart from FLIR? The shallow well depth sensor does not seem available in any FLIR cameras, so that may be one advantage. What other advantages do you offer for ultra short exposure applications? And that's the end. So.
I can answer that one. So I don't want to speak for all of FLIR, right? But traditionally, we see that they don't like to do custom configurations. They're typically not interested in exploring one-offs for specific applications, where we, on the other hand, are. That's exactly what we're doing now with several of our customers in the hypersonic space, and that's why we've made this presentation. So we have pushed our cameras below the standard specs. I think at a certain point, in the near future, our exposure time minimums will be lower than anything else that is offered by any IR camera company. And we're actively working on this. We are a company of scientists and engineers, and this is what we love to do. So I would encourage you to team up with us, to reach out and to help develop these really powerful new sensors and technology.
Yeah,
another one in there?
Yeah, we have some more coming in. Great presentation. Could you elaborate on the characterization of the rest of the fast MXK, so M1K, M2K, M3K cameras?
Right. So the M3K is obviously going to be the most interesting for this, and it's because of those 30 micron pixels, the pixel pitch. It really allows us to get good radiometric performance, good signal to noise as we push the exposure time further. Excuse me. We're also considering the M1K, the M2K UD variants for similar purposes. It gets to a point where those are just the best cameras. The other cameras are sort of lesser in true top-end performance. It's not necessarily that they wouldn't be able to perform under 1 microsecond, but the M3K would perform better. So that's what we've explored so far.
All right. Oh, yeah, it was just a clarification, basically. of that question. So we've been trying to push the M1K into very short integration time range. So I don't know if you've been discussing with Telops people about this, but like Joe mentioned in the webinar, it does vary from camera to camera, and there's been some work into pushing that limit even more. So another question coming in, why did one camera have a blanket on? Are you warming, cooling it? Will that affect the calibration? That's an interesting story. Joe can talk about that. That was in New Mexico, I believe.
We were in the desert in New Mexico in June, and that was a mid-wave camera. So it was just to help the cooler out a little bit. I don't know if you've ever used a cooled infrared camera, but they purr really loud. It really strains the Stirling coolers when you're at those extremes of the working conditions. So we were just trying to help it out a little bit. The camera next to it that did not have a cover was a shortwave camera that it operates at a much higher temperature. It does not have the same internal cooling requirements. So if you are in a desert, talk to us about the shortwave too, but traditionally we're looking midwave for these applications.
Another question coming in. So why are our camera's resolutions so limited? Someone saying, I want 4K our images. That's basically our cameras are always basically at least a decade behind visible cameras. I don't know, Jeff, if you want to talk about this a little bit more.
Yeah, I mean, the main problem is as you increase that detector size larger, you have to increase the size of your cooler larger, you have to increase your readout electronics. It becomes very expensive very quickly. If you have extremely deep pockets, we have thought about this. We do have the concept for a 4K camera, but the development project would be very, very, very expensive. So yeah, again, same to what Antoine said. Infrared cameras are traditionally a little bit behind visible spectrum cameras, and that's due to market size and the amount of R&D money that's available.
Very true. Let's see. Last question may be coming in. Do you design your own ROICs and FPAs? It's a very good question. Sort of in between here, Joe, if you want to talk about
that. Traditionally, no. In most of the cameras, we do not. But in some of the cameras, they are designed by us, specifically the ROICs. It's an advantage on some of the cameras that we have more options to play with the firmware on the ones that we've developed ourselves as well. So it's not yes or no, unfortunately. If you have a question about a specific camera, you can send another message or send us an email, and we will get you the exact answer.
Okay. Oh, okay. Well, we had that one last question coming in, and then I think we'll wrap it up after this. If you're operating in an environment that is much colder than the minimum operating temperature of a Telops camera, would you recommend a heated blanket? Do you think the calibration would still be useful if you artificially change the internal temperature this way?
Well, so let me jump on that. Yeah. I already have an idea of where you're going. I would say to reach out to us immediately, right? The multi-point calibrations that we are planning for these sub-microsecond exposures could, in theory, be done at the specific temperatures you expect during the time of your measurement. In fact, that's actually what we'd want to do. So it wouldn't necessarily require a heated blanket or anything like that, but we could just calibrate the camera at the extreme low temperatures that you're talking about, as long as they're not ridiculously low extreme. At a certain point, I'm sure performance would be relatively not possible, but we'd be happy to talk with you about it, is the answer.
Great. Well, thank you very much, everyone, for those great questions. And thank you once again to Joe for this great webinar. If you've registered, we will send you a thank you note with all the questions and a link to the video that will be available on our YouTube channel. So thank you very much again, and have a great day, everyone.